Okay, do you hear me? Okay, good afternoon. Thank you, Guillaume, for the nice introduction. Um, I'm very honored to give the keynote talk on the, especially on the ECRF's user meeting, because for us as the users, it's very important to use the facilities. And in our kind of research with the diffraction studies at extreme conditions, the user synchrotron facilities is absolutely needed. So that's why before going in the depths of my scientific project, I would rather spend quite a bit of time on explaining the details of these techniques, and I hope that you will be fascinated with this. Um, so our studies are involving extreme conditions, extreme pressures and temperatures. So first I would like to just agree on the units. And for the temperatures, it's more or less understandable what extreme temperature means. Everything which is not 300 K is typically either too cold or too hot. But for pressures, it's not very obvious. So for us, of course, the comfortable pressure is 1 atmosphere. And it's typically in the Pascal units, it's 10^5, 10 power 5 pascals. In our high pressure research, we also use units of gigapascals. So it's 10 minus fourth of there. So 1 atmosphere is 1/10 minus fourth of the gigapascal. So 1 gigapascal is 100 atmospheres. So just to give you some context, how high is that? So if you have an elephant that just exerts pressure of around 10 minus 4 GPa, and in comparison, the heel gives a very high pressure, so 100 times more than elephant actually on the floor. If you look on the deepest part of our planet, Mariana Trench, so these 10 kilometers of water create the pressure just 1/10 of the gigapascal. And that's actually the starting pressures which we are interested with. So by the reference, the pressure inside our planet in the center is around 360 GPa. And for example, in extraterrestrial rocky planets that were discovered in the last decade, like now it's about 5,000 of the extraterrestrial rocket planet with possibilities of life. So the biggest ones, the pressure inside could reach thousands on tens of thousands of GPa, and the temperatures as well, thousands of Kelvin. Oops. And of course, for geoscience research, it's important to understand what processes can happen at these extreme conditions that can influence on the plate tectonics and the appearance of life on these planets. But also for chemists, as I'm a chemist, it's also important to look at the possible chemical reactions and changes in the physical properties that can be induced by extreme conditions. And that can be very substantial, because if you look just on the enthalpy value, we have so-called PEWV term, and the pressure, the higher the pressure, the higher the term it can provide and can stabilize very interesting structures. So even 1 GPa is equivalent to about 1000 Kelvin. And for the normal chemist that works not with such high temperatures, that can create quite a way different chemistry. So imagine what happens if in the case of way higher pressures. And in principle, for human civilization, applying for pressures in the chemical synthesis is not something new. So very famous Haber-Bosch process, that's the reaction between nitrogen and hydrogen forming ammonia. That was a source of their synthesis of the fertilizers. So just a huge step for industrial revolution. And that happened at just very small pressures in our scale, just 200 atmospheres, a little bit higher pressures, and you can already achieve their high pressure food pasteurization without applying any chemicals. At 5 GPa, you can synthesize diamonds from graphite, like synthetic diamonds, and also use them in the industry quite a lot. Even a small bit of pressure can actually induce quite a lot of the interesting properties. So just 20 GPa, already the pressure starts to change our structures. That first is reflected, for example, in changing the crystal chemistry by changing coordination numbers. So the structures adopt to high pressures to dense more dense. And typically, the amount of atoms around certain atoms also increases. So you can have, for example, increase in coordination of the carbonates. So typical carbonate and the room pressure will have carbon will have 3 oxygen atoms, and at high pressure, it have 4 oxygen atoms. Many things are connected also with polymerization, especially for the light elements. Famous example is sodium chlorine 3, and not because of the weird oxidation number, but just chlorine makes the polymerization. So chlorine 3 units at high pressures. Similar things appears in carbides, in nitrides, and in even more complex molecule like carbonates that can also form polycarbonates molecules. You can get many new compositions stabilized by high pressures, many new oxidation states also stabilized by high pressures. And at pressures even higher, you can have very interesting physical properties. The most, of course, famous is the superconductivity. So, for example, in hydrides, you can reach near room temperature superconductivity above 100 GPa. But how to study this phenomena? How to generate pressures first? So just give you some overview. Pressure is very simply defined. It's just force divided by area. So you can either create a lot of force, that's a pathway of the huge devices, such as large volume apparatuses, as a piston cylinder, pedicel in Brussels, or huge large volume presses. They all tend to create huge pressure on the sample, but they're typically limited to pressures about 30 GPa. Way more effective way to produce pressures are actually other ways, just to decrease the area. And that's realized in the devices called diamond anvil cells. So if you reduce the area, you can, with the same force, produce way higher pressures. And then in order to sustain this pressure, the materials which you created should be very, very hard. And we just take the hardest material ever, so diamonds. So typically in these experiments, you have 2 diamond anvils with the plates here called culettes, and the surface of, and between these diamonds, we have a thin layer foil where we drill a gasket in between. And this is called pressure chamber. Inside this pressure chamber, we put our sample, and then we load this with the liquid media. We do not press on the sample directly. We transmit the pressure from the diamond to the sample through the pressure media. And in order to create pressure on diamond, we have a metallic body around this. By rotating the screws, we create some force, some hundreds of newtons, and then this transforms to the GPAs and hundreds of GPAs. Nice thing about diamonds, they're transparent, and that allows to use huge amount of techniques. And here, as you can see your sample, so that's typical pressure chamber. I think it's around 50 GPa. You can see the sample very nicely, and the pressure media, which is inert gas here, neon. If you want to go to way higher pressures, of course, you can decrease the area further by, for example, introducing secondary anvils. That's a half spheres where these half spheres touch, and between them there is a miniature sample. And here in the submicron area, you can develop pressure up to 1 terapascal. Of course, this requires from the person very huge dedication in assembling those, and this kind of one-time experiment in the life, because you don't want to do this for the second time. Another approach is just machine diamond anvils themselves and give them a certain shape, like, for example, toroidal anvils, where, again, the size of the culet will be effectively way smaller, like 10 microns, and in between this, you can put your sample. That's maybe also possible way. So these ones, so-called toroidal anvils, they produce pressures on the order between 500, so below 1 terapascal. Also, you can combine that with the heating or with the cooling. So you can put cryogenically cool your cell up to helium temperatures. You can do the resistive heating around the diamonds, but that typically limits the available temperatures to 1200 K, because after that, diamonds just start to burn and graphitize. That's why there is another way how to produce temperatures. Just use 2 infrared or CO2 lasers that have a spot around 10 microns, the size of your sample. And then you apply from upstream and downstream side their laser, the laser power, and then the sample can hit. And from the color of this emitted radiation, you can estimate the temperature. So this one was above 3000 Kelvin, I guess. And of course, since our samples are very, very small, for us, use of their small focused beams is just unavoidable. So, and luckily at ISRF, there are lots of their possible techniques with which one can study the materials at extreme conditions. I took that from the ISRF page. Many beamlines provide opportunities to do studies in the high pressure environment. And major techniques are typically diffraction, synchrotron Miss-Bauer spectroscopy, Raman scattering, nuclear resonance scattering, absorption emission spectroscopy, and so on. So I will talk about mostly of the diffraction methods and how one can apply them to study the chemistry in their diamond anvil cells and various chemical processes. So for that, for the diffraction, applying the diffraction in diamond anvil cell is typically two ways. One is the use of powder samples in it, and another way is using single crystal samples in it. So powder samples, you just put the powder in the whole pressure chamber, then compress and expose with X-ray beam and get typically the images intensity versus diffracted Bragg angle. And in principle, this way of doing experiments is very easy technically. With this method, you can really achieve very high pressures. So 1 terapascal was first obtained on the powdered sample in 2016. But it has its own drawbacks. In the ideal life, of course, we want to have a very nice resolved peaks, and that will allow person to solve the crystal structure, ideally refine the structure, atomic positions, and so on. But in reality, it typically looks very ugly because when you use the powder, there are many single crystalline grains inside. And with the pressure, these grains start to compress on each other and develop as strains. And that's negatively affects on the image you get. So sometimes it's even not clear whether you have a transition in the sample or not, or whether it's chemical reaction. We're not talking even about determining the structure from this. Single crystal XRD is another way. So you apply as your sample single crystals. For many years, it was less used because single crystals, you need to grow one and just compress it, and they are sensitive to compression. But right now, with decreasing the size of the diffraction beams, with the synchrotron beams, we can study smaller and smaller crystals approaching to the size of powders. And also by developing with a new software appearing to process these samples, it's becoming way, way easier to do single crystal on the sample. And as a result, 1 terapascal was reached also in the single crystal just very recently, 3 years ago. So just a couple of words about the technique. In the single crystal XRD, we expose the single crystal with the X-ray beam. And we collect the resulting image with the two-dimensional detector. And on this two-dimensional detector, you typically have a set of the reflections that is just a slice of your reciprocal space. By rotating the crystal, you can get another slice of the reciprocal space, and so on and so on, until you can get the full reconstruction of the reciprocal space. And that's beneficial because from this, we can determine structural information about our crystal. So distance between these peaks, so that's a reciprocal space image. For the single crystal, it should be just equivalently positioned peaks in the space. And distance between peaks will give you unit cell parameters and symmetry. And the intensity of these peaks will provide you information about atomic coordinates and the space group. And basically, that's everything you need to know to reconstruct, to get the whole information about the crystal structure. That's how it looks like, the reciprocal space of the one single crystal grain in the software we use for data analysis. So you see these equivalently spaced peaks in their reciprocal space. So, and that's now let's imagine that we have not only one crystal, but two crystals. And what we will have is just overlay of the two such lattices in the three-dimensional space. If we have by chance 3 grains, we will have a little bit more complex picture, like 3 grains. And in case if we have powder, which is simply just thousands of the single crystal grains, you will have the set of these concentric rings, which are just sum of these three-dimensional lattices. But the nice thing for the single crystal XRD is that in the software particularly, that you can just select, manually rotate this reciprocal space, search for the rows of the reflections, then you select some that you see their pattern. You need like 20 picks, not hundreds of that. And then the software can calculate the unit cell parameter, orientation of the crystal, and then can find the rest of the reflections. And then by using this information, we can again solve the structure. And that doesn't matter whether we have one single crystal, many single crystals, doesn't matter whether we have several phases with different unit cell parameters. We don't care, because we just can extract this information directly from these reciprocal space reconstructions. Previously, we did this manually, selecting the peaks, but right now there is a software, 3 years ago, it appeared software written by Andreas Landukov and his brother, that allows to do this search for the grains in minutes. So we can find hundreds of grains, check them whether it's the same phase, whether it's different phases. From each of them, we can determine the crystal structure, and applying some crystallographical knowledge, we can also reduce the chemical composition, even in very complex cases. So that's typically how our experiment looked like. So this is our diamond anvil cell. So we are interested in the performing certain chemical reactions. That's why we typically put some reacting agent, this black particle, and we sandwich it with a pressure media that also serves as the second reacting agent. So before the heating, we in principle know what we put. At least I know what I put. Sometimes my students don't. But after the heating, we typically don't have idea what happens. So we have some crystallographical knowledge, but it doesn't work in 100% of the cases. So what to do next? We do the X-ray method. We select the region where we laser heated our sample. And then we do so-called X-ray diffraction map. So we measure diffraction pattern in every, let's say, every 2 microns. So this spot, then step another 2 microns, another spot, and so on. So we have just simple powder XRD images, just 2-dimensional ones. And from these images, we determine whether we have nice single crystals or not, whether this pattern is have certain new peaks. If it has certain new peaks, we do a single crystal data collection in certain particular spots. After that, applying these new techniques of the finding grains, we solve the structure of all of the phases which are inside, which correspond to these particular spots. Then we go back to our XRD map and check whether we can explain all of the reflections on the powder pattern with these phases. If not, we repeat again and trying to search the remaining phases. If yes, so we can use the information to make this phase maps. So to just place the special distribution of the phases that formed after the laser heating. Yeah, so you can see this distribution of various xenon fluorides after the laser heating. And this black spot was actually gold that was used as a heater, not that is reacting agent. And that was a type of the so-called cook and look experiments, where we just laser heat our samples shortly for seconds. We have our reaction, and we turn off the laser, and we study the products of the reaction. The products are still under the same pressure, but they are not at the same temperature that was during the synthesis, so-called quenched reaction. Of course, if we are interested mostly in the geological processes, which occurs also at high pressures and high temperatures, for us it's beneficial, of course, to make such experiments during the heating. And that appears not to be a very easy not very easy to implement because in typical single crystal experiment, you rotate the single crystal, but as well, you need to rotate the lasers. So lasers just stay in the same position during the heating. These setups are realized right now only in 2 places in the world, and in DAISY and also at ISRF at ID27 beamline. And they, in principle, allow to do such kind of experiments. So you rotate the lasers together with the sample. So this is one of the first results obtained with such a system. That's heating of the iron in nitrogen. So you see some powder initial agents without the heating. And during the laser heating, you see appearance of these spots. They correspond to a single crystal that are forming at this 1000 Kelvin. So the temperature was around 1000 Kelvin in this case. So we could solve the structure both during the heating and after the heating, and got the same crystal structure. And compare also unit cell parameters. We see that due to thermal expansion, our unit cell parameters are bigger. And also we can see the same for their thermal ellipsoids. So even from them, we also can see the temperature effect. What is also important, of course, pushing the limits and trying to go as high in pressure as possible to study no other possible chemical reactions. But of course, if you go high in pressure, so our typical pressures are up to 100 GPa. But if you approach 200 GPa, that's already very tricky because the sample sizes needs to be very small, let's say below 5 microns. And in order to study that, you really need very tightly focused synchrotron beams. Just as the possible demonstration, so this is 3 diffraction patterns collected on the same sample with a different size of the diffraction beam. So it's FeO compound at 200 GPa. This is the first sample collected with 10 by 10 micron diffraction beam. So these huge powder rings, they correspond to the metallic gasket. Basically, it's not our sample. That's something around our sample. This huge peak here is also not our sample. That's a diamond. That's the diffraction of the diamond annual. What is from our sample is that subtle small reflection and maybe something like this. From this, you almost don't see any diffraction. If you start to decrease the, we start to tighten the focusing, decrease the beam size, we start to see 2 weak powder lines, these 2 things here. But from that, again, from 2 powder lines, it's really hard to determine unit cell parameters. You can only approximate and just make some guess. Maybe it's some cubic. If you don't have so many peaks, maybe it's highly symmetrical phase. But if you go to the beam line that has way tighter focusing, 0.4 by 0.4, that's possible now at, for example, ID11 beam line, then you start see the reflections belonging to the single crystal grain. So here, these separate spots are from one single crystal grain. And these are very nicely diffracted crystals. So from them, we indeed could solve the crystal structure and understood that it's not cubic, but rather orthorhombic one. So a summary for the methods, I just like to tell that synchrotron facilities really can help a lot in study high pressure behavior of materials. So and single crystal diffraction really can provide valuable information about studying chemistry of the materials. So we can do these studies in situ. We don't need to decompress the sample and try to understand what happened at these high pressures. And now I'd like to, and with single crystal XRD, we don't need to know any prior information basically, except of possible elements that are inside. So, and we don't care if it's polycrystalline or multi-phase mixture. So with that, I would just like to demonstrate how we can study real materials, and that's the system of FeOH. So first, I will just show some results on FeO, easier system, and then just tell about FeOH system. So FeO is just archetypal example of the binary system that important was for the Earth and for the solid state physics. So iron oxides are ion members of various geological series for various silicates, and iron is the only element that has various oxidation states among these elements that form our planet. So typically iron 3 plus is mostly located on the surface of our planet because oxidation of by oxygen atmosphere. Most of the iron 2 plus is located in the lower mantle, and iron 0 is located in the outer core. And since it's the only element that has different oxidation state in the Earth and presented in all of the layers, it controls basically all of the redox processes that happen in our planet. And as well, under high pressures, it has lots of the interest in physics, so interest in chemical and physical changes. And that's why it's also important for the solid state science. So really, iron oxides are exhibit very, very rich chemistry and crystal chemistry. Also because having several oxidation states. Every oxide with this different ratio of oxidation state can have different high pressure phases. Also, there are huge possibilities to have very weird iron oxygen ratio in these oxides stabilized by different pressures. And in principle, there is also a possibility for oxygen change the oxidation state and stabilize oxidation state lower than 2 minus, and for example, to 1.5 minus. That's realized in FeO2 compound. I will just discuss it a little bit later on. So I will not be talking about all of these compounds. I just want to show some systematic how to navigate through all of these various differently structured compounds and maybe just give some brief overview of the possible rules that govern their formation. So easiest is the understanding their crystal chemistry, how they are formed. And many of them formed very simply from very simple building blocks that just combine in different way, like Lego constructor. So the typical building blocks are FeO6 octahedrons that connect to the slabs in the layers. They are shown here by brown color, and also FeO6 prisms or capped prisms that have additional oxygen coordination, but so far it's not very important. These can connect through common triangular bases in rods. And in principle, you may have a series of homologous compounds where you have just these slabs and rods combined and with the different ratios. And you start like with wüstite, where you have only FeO6 octahedrons and just iron 2 plus. And adding more of these rods will give you more and more iron 3 plus. But it doesn't mean that iron 3 plus is located here and 2 plus is here. No, they actually are mixed valence compound, and any iron 2 plus and iron 3 plus don't have much of the preference. It can occupy both of the positions. So a little bit more complicated is this one. It's not so obvious how they're connected. It's a little bit more complex way of connection, but in principle, the blocks are the same, just connected differently. And they also can form the series of the different but similarly structured compounds. So that means that in principle, this system is very rich in the compositions because it's very simple for the building blocks to connect to each other. And that gives a rise to this huge amount of compounds. What also happens if you just look on the behavior of the individual compounds with pressure, typically what happens is increase the coordination number. So if you look here, that's the behavior of magnetite, if it's 3 or 4 with the pressure. So you start typically with coordination number 4 and 6. And with higher pressures, you go first to the 6 coordination number, then 6 and additional coordination, like 7 here. And if you go a little bit higher in pressures and temperatures, you start stabilizing some distorted polyhedrons with the higher coordination number equal 8. All of that is done in order to optimize the positions of atoms in the crystal structure to make the structure denser as a response to the high pressure. So you see how the volume of the compound just decreases drastically if you just change the coordination number here. it just drops here and further away. Fe2O3 is another example where everything can be even more complicated. Um, this compound also undergoes a structural transition to optimize the crystal structure with pressure. And volume pressure change is very huge, around 10%. And it's also not only also because of the structural change, but there are lots of the other changes happening during this transition, such as spin crossover from iron in high spin state to the low spin state, and low spin state radius of iron 3 plus is way smaller. That's why you have such a high change in the volume. But in addition to that, that accompanies with the collapse of the magnetical moment. So this data we obtained on the Nussbauer, synchrotron Nussbauer spectroscopy beamline here, TSRF. Yes, so you can see that instead of magnetic compound, you have a non-magnetic one. So all of these changes in the iron oxides are important to study our planet. So although Fe3 plus iron oxides are mostly connected on the surface, there are some studies showing that these compounds can be delivered to the deepest interiors with in the process called subduction. So typically it's like a heavier slab that go in deeper. And there are some slabs that contains quite a lot of the iron that's called these are so-called banded iron formations. That's the main source of the iron for our civilization. That's basically iron oxides embedded, sandwiched between SiO2 layers. And then can indeed be subducted in the interiors and even reach core mantle boundary. And certain studies suggest that they can be a source of the strange behaving zones on the core mantle boundary where you have low density of the seismic waves. So so the study of these materials, what happens with them, with iron oxides at extreme conditions, is important to understand what happening with this oxide within these bending iron formations. And what happens with them at high pressures and temperatures, they not only change the structure, but they tend to decompose at around, at the pressures of the lower mantle. And typically they just decompose in a very interesting way that the final chemical compositions, regardless of what we started, it ends up to the Fe3O4 or compositions closer to Fe3O4, either with release of iron or either with release of oxidizing surrounding materials. So it's written here like oxygen, but nevertheless, it's just very stable composition at this pressure. If we add some hydrogen in the system, it becomes even more complicated. Because on top of these structural changes, the water can, of course, change the chemistry quite substantially. And the importance of the hydrous materials for the studies of the deep interiors, so it's indeed very important to study how they behave in the deepest interiors, because water can influence on their such parameters of the viscosity. Typically, more hydrous materials are less viscous. They promote their better heat transport and also electrical conductivity. So lots of the heat of the core can be transformed to higher layers. So, but the question, what possible water carriers can be inside the Earth? And quite a lot of the research was sparkled by the synthesis of so-called pyrite structured iron oxide. This compound, if it's anhydrous, have following crystal structure of pyrite, FeS2. It composed of FeU6 octahedrons connected through the common edges. And while in pyrite, iron oxidation state is 2+, several studies show that here in the oxide pyrite structure, iron have oxidation state 3+. And oxygen then have very weird oxidation state 1.5-. But what's interesting for this compound is that it can be also accommodate quite significant amount of water in its structure. This compounds FeO2H. You can synthesize these compounds either by thermal decomposition of FeOH at high pressures and temperatures, or by direct reaction of iron with water. So, which is just schematically shown here. It's several studies show that you can perform this reaction at around 80 GPa and stabilize hydrous material in the deepest material conditions, meaning that it will be stable at these conditions and can be a possible water carrier. But you also need to consider that you need to bring this compound into deepest interiors, and then it's not so nice for the FeOH because at the lower pressures, it's actually could be decomposed very easily. So of course here it's stable, but at the lower pressures, it just decomposed to anhydrous materials. So it was not very clear whether you can stabilize this at lower pressures. And that's why we decided to perform experiments on just synthesizing hydrous materials in the water-rich environments. So we just took simple anhydrous iron oxide in water and then just tried to see whether we can synthesize hydrous material. You can synthesize it by decomposition of the hydroxide. You can synthesize it from pure iron and water. So what happens if you do the oxide and water? And as a result, we synthesize this new iron oxide Fe8O11 with their FeO ratio very close to Fe3O4. Again, this magic ratio at relatively mild pressures. So again, it's a new member of homologous series, again, octahedrons and prisms. In principle, you can synthesize this compound as well at 76 GPa by thermal decomposition of not anhydrous Fe3O4. So this is water-free environment, and this is water-rich environment, but we get the same composition. So the question is whether indeed we have any water inside. So to answer this question, we in principle can do such kind of plots where we plot the density of the material as a function of the iron content, atomic iron content. So on this side, for example, if we have pure FeO, we have its density, and the iron content is FeO is 50%, and 1 atom of iron, 1 atom of oxygen. So if here will be FeO2, the iron content here will be 33%, 1 atom of iron, 2 atoms of oxygen. And then the densities, if we plot another densities of the other iron oxides at the same pressure, so in principle, they will follow more or less this trend. So if something is having hydrogens, typically it results in densities, so it's way less dense. So if we do the same plot for epsilon FeOH, we see way big change so way smaller density here. So if we plot our iron oxide, so we do see as well that it's more likely doesn't have water or have very minor amount of water. So it cannot be the water carrier here. And it's very strange. Indeed, if we just simply put it in the water, it doesn't take quite much of water there. On the other side, at the same conditions, if we take just iron hydroxide in water, we synthesized almost several new hydroxides and also pyrite structure, FeOH. Yeah, so if we plot the densities here, we see that their densities are way, way smaller than corresponding densities of the oxides, suggesting that there is some hydrogen inside. So it's really depending on what the starting material will take. And in water-rich environment, in principle, we can also stabilize the FeOH at lower pressures and synthesize any other new water carriers. So the crystal structure of this compound is similar to it is also following certain homologous series, a little bit different than other ones. So, but it applies the building blocks of nominally anhydrous iron oxides. So you can just see these elements of the constructor shown with the different colors. So in principle, that's again suggesting that we can have another iron oxides in this system. But what also should be considered in these water reactions is, of course, the diamond anvil cell itself, because it also can give you lots of surprises. So what can happen if we, in addition to what the phases I have shown, it's not so easy environment. So by surprise, we also get rhenium iron oxides inside, and rhenium typically comes from the gasket. So we have this metal foil, and the water, since it's nice solvent, it also brought some rhenium there, and we can also get some mixed iron oxide. And the carbon from the diamond also likes to react. So in addition to this oxide, we have a new iron carbonate here, also hydrated. So that can be a possible water carrier, yeah. Yeah, but the advantages of the single crystal XRD there is that it can effectively filter all of these things. It can effectively find what is that without, whether it's synthesized by surprise or by the mistake, you can always can understand what you're getting without opening the cell, doing a CM. So you can do that by applying crystallographical knowledge. So, and that's just like to conclude. So just hope to convince you that iron system is very rich system in terms of their whatever crystallography, chemical compounds that can form. And there are also interesting electronic and magnetic properties that I didn't cover much. And also the presence of water in iron oxygen system can really change the reaction, how it goes. And in principle, applying this knowledge, we can try another pressure medium, trying to govern the reaction in other directions. Because for diamond anvils, it's very difficult to, for example, control oxygen fugacity or various conditions in the cell. So just small promo is that we are also, for those who are interested in methods, how to do this multi-grain crystallography in the diamond anvil cells, we are organizing their summer school in Frankfurt from the 3rd to 8th of August 2025. That will include hands-on sessions, tutorials, and lectures. So it will be about 30 participants. We will start the registration in March. Yeah, so by the end of this 1 week school, we expect that person can be able to process this multi-grain data set and do all of the data evaluation himself or herself. So one who is interested, please apply and see you in Frankfurt. So, and just as acknowledgements, I'd like to acknowledge all of my collaborators, especially SREF for providing the beam time so that we can do our precious studies. And I would like to thank you for your kind attention.